This is the ROS Developers Podcast, episode 110.
The ROS Developers Podcast, the ROS Developers. The ROS Developers Podcast, the ROS Developers.
Hello, ROS developers, and welcome to the ROS Developers Podcast, the program, the podcast that gives you insights from the experts about how to program your robots with ROS. This is Ricardo from The Construct, and today I would like to dedicate this episode to all the ROS developers out there that have started or they are already in progress doing some progress programming robots by using FPGAs and accelerated hardware of any kind. So if you are any of those engineers, any of those ROS developers using accelerated hardware for your robots, click Victor Mayoral, for example, this episode is dedicated to you. Okay, very good. Today we are going to learn a lot more about accelerated hardware for robots. But before that, let me tell you about the training program that the Construct has created in order to make you learn about ROS2, prepare your robots for being ready to work with ROS2, or even to manage fleets of robots. We have created a series of trainings for in 3 days, live trainings by using real robots connected in Barcelona. So those are trainings, online trainings that you can access with the teachers. The teachers are based in Barcelona. You can be anywhere in the world, and you will be connecting to our robots in Barcelona and practice with our robots. We have built even a complete cafeteria where you can practice with those robots of the cafeteria, or we have built also a small warehouse, and you will be practicing with warehouse robots there in our online trainings. So if you are interested to start training your teams, for example, during the 2023, then check the link I will put here on the description of the video, and we will be very happy to teach you about how to program your robots with ROS2. Great. So having said that, I think that you will be very, very interested on the subject of the podcast today, because this is the first time and the podcast that we are delivering this subject. And the subject is about hardware acceleration. So for this, we have here today with us Giulio Corradi, who is the principal architect, industrial vision, healthcare, and science at AMD. Giulio, welcome to the podcast.
Thank you. Welcome.
It's my pleasure. So we met at the ROSCon of this year, right?
Right, correct.
Yeah, you were doing a presentation also.
I was just a panelist at ROSCon for functional safety, because functional safety is one of my specialization within the company, and specifically in robotics. Yes, correct. So it was a great event, a great ROSCon, I would say.
It was your first ROSCon?
It was my first ROSCon in person, I would say, because the previous one was something virtual. But definitely worth to be there, and extremely useful, I would say. Very good.
Awesome.
Very good.
Very good. Yes, it was very good. And then we were talking about accelerated hardware, which is the subject that we are going to talk today. But before that, tell me about your company, because the company is super famous, is AMD, and AMD company recently acquired Xilinx company. So how does the combined company better address the needs of robotics developers?
Yeah, correct. So fundamentally, I belong to the Xilinx company, so the company that has been acquired. So in February this year, AMD basically acquired Xilinx, and the combination of the two technologies, the AMD classic technology that has CPUs, x86, and GPUs, the technology from Xilinx that's is FPGA and the system on chip for embedded. It's a very powerful combination of the two, and definitely it's offering I would say a sort of end-to-end solution for robotics, because, for example, you have a very powerful embedded system that could acquire signals, process signals within the FPGA. I can maybe illustrate a little bit better later on. And then you have a processing pipeline composed of embedded CPU, or I would say x86 CPUs that could, create the proper computational activities in basically offering, for example, for ROS, the proper infrastructure. And then you have GPUs, and GPUs are offering, the possibility to implement AI system, offering, a massive acceleration. So we have basically the full pipeline, and those things are going from acquiring a signals or controlling a motors or, making everything that is related to the hardware portion of the mechanical portion of the robots up to the most computationally intensive system. So it's definitely a very, very, very good combination. And in my opinion, is the unique combination, because we have the full pipeline.
Awesome. But then just to clarify for the audience, so then GPU that you mentioned and FPGA, they are different things.
Absolutely. I mean, they are different things in the maybe FPGA. GPU is much more well known. The FPGA maybe is a little bit less known, so it's probably important to spend a little bit of introduction on the FPGA. FPGA fundamentally is a programmable hardware. So you design your hardware using software. It could be a specific language that has been, used since more than 30 years to design the FPGA, that are hardware languages. But today, the evolution of all the tools allows, for example, C and C++ to be compiled directly into hardware. What does it mean? It means that you can create, for example, parallel systems that are deployed directly into this particular hardware, and every operation is executed every single clock cycle of the machine. So you can have an extremely high parallelism inside a very small embedded device. So this is fundamentally the difference. So the FPGA has another capability compared to the GPUs. The GPUs is very powerful in the computational, activities. The FPGA offers, in addition to that, the ability to provide time-bounded operations, so determinism, synchronization, and direct signal acquisition from the field. And that is fundamentally very, very important for robotics, because robots are interacting with the real world, and you need a very fast response. So the FPGA has this kind of ability: I/O, data processing, data movement, data offload, acceleration. It's in general, I would say, not that straightforward using GPUs. GPUs are formidable machines for acceleration. Yes. But the FPGA combines basically acceleration and massive capability to process signals in a deterministic way. I can give you a little bit of more information, maybe if we enter into some specialized topics in this conversation.
In the talk, okay. Then let's go step by step. So that's a very good introduction for the differences between GPU and FPGA. Yeah. Even if you mentioned that the products that AMD produces, also in combination with Xilinx, also, then it contains the whole bunch, so including GPUs and FPGAs also.
Let's put this way: it's a full pipeline, and then you map the specific product within the specific application. So what concerns the robotic part, right now we are focusing, I would say, in a specific embedded platform that is a combination of a processing unit and FPGAs all together. in order to provide a specific acceleration and a specific, let's say, I/O and determinism and communication. This is what we are focusing right now. All the rest, I would say, is part of a system level application. So if you have your workstation or your main controller, it could run into an x86, it could run into an embedded platform. And if you need to train a network, it could run, I mean, a neural network, it could run into a GPU. So it depends on the system level application. But from today, I would say the focus is on the embedded platform, the KR260 and those kind of platforms that are enabling roboticists to get much more control, I would say, in their application, especially, as I said before, processing signals.
Okay. So you are mentioning now the KR260.
Yes.
So this is the product that attracted my attention, and I especially contact you for this interview, which is you recently released. It's called the Kriya KR260, which is marketed as a robotics starter kit. So what is that concretely? What does it contain?
So KR260 is basically an embedded platform that is offering, you know, the ability to combine a ROS-enabled system plus, I would say, this specialized hardware that is the programmable logic, all contained into an embedded platform, and has all the interfaces that are normally required for a robotic application. So a video interface, a networking interface that is extremely important, because the KR260, for example, supports the industrial networking, supports as well TSN, so the time-sensitive network, that is becoming one of the most important, let's say, communication mechanisms looking in the future. In addition, for example, to support the standard communication like EtherCAT or Profinet, those kind of things. The KR260 is also supporting a sort of backbone if you need to transfer a significant amount of data, because it's offering 1 gigabit communication plus 10 gigabit communication connectivity. So those kind of things, you know, a robotics system is in general a distributed machine. You need communication, you need a very efficient communication, and that is one of the primary focus. The other focus is providing all the different interfaces, for example, for inertial measurement unit, IMU, or whatever type of protocols. For example, there are many grippers, many manipulators that are using still, you know, RS422, RS485 communication with the specific protocol. So it could be adapted. It has already a native support for those type of things. In addition to, you know, the FPGA and the proper acceleration. So it's a machine that, as I said before, it's combining two things: enabling the communication, enabling the signal acquisition, processing those signals, having the ability to process those signals in real time, and that's what KR260 is offering. It's definitely a development platform, so it's ready to be used. It comes with a support of operating system, so it behaves like a workstation, an embedded platform, and a very powerful signal acquisition system. So it's a very unique, I would say. It's very. I mean, there is no similar product today in the market. I dare to say.
Yeah, I was going to ask you about the difference between the Kriya KR260 and, for example, some other existing ones, but you mentioned like Jetson, Nano Ejection, all the Jetson family from NVIDIA.
The difference is fundamentally, as I said, is a profound difference, because those systems are designed for computing, you know, processing, and as I said, acceleration, just let's say video or some sort of other type of operations. The KR260 is a superset of that. So it offers the acceleration, the hardware acceleration through the programmable logic, as I said before. So you can compile a portion and offload, I would say, a portion of your system into the FPGA, such that there is a gain in terms of speed up or in determinism. But it's also combining the communication systems. So the communication, as I said, is very, very important. One of the most, I would say, critical parts, for example, in ROS and ROS2, is how you handle the timing, how you handle the communication, how you handle the the predictability, the determinism. And if you, for example, if your application is not capable to support the proper, say, real time and combination, as soon as the application is becoming more complex, it requires much more powerful. So communication is taxing a lot the CPUs. The KR260 is offering a way to offload this particular mechanism into the FPGA, and we already provide this particular support with TSN, as I said before. So this is the major difference compared to the Jetson. Definitely, all the other products have their advantages and their capabilities, but in order to be very, I would say, close to a mechatronic system that is a robot, is a combination of mechanical parts, things that moves, things that sense, things that are actuating. You need a platform that is dedicated to this particular task.
Okay, so if I have correctly understood, then let's say we have an application which is a humanoid robot that has to walk. And for that robot, for example, having real time is very, very important, because otherwise the next step is going to make the robot fall if it doesn't execute the proper position at the correct time, right? It's going to fall. Then in let's say in very typical applications, we have been using a normal computer, a usual computer, which we patch for accessing real time, and then we do some other tricks in order to achieve this real time. By using this kind of accelerated hardware, then we can forget about all those patches, all those tricks, because the hardware itself is already ensuring that the real time is achieved, right?
Correct. So the point is, you partition your application in a way that the determinism, so the portion that is hard real time, and let me define what is hard real time. Hard real time is something that requires a precise, timing behavior. Jitter is exactly as you are doing right now. So schedule it very precisely. So the programmable logic allows you to create algorithms that are very much scheduled on time, extremely to the nanosecond level, if you will. And at the same time, the ability to have those algorithms that are handling or moving data in and out to the memory and in and out to the standard, I would say, I/O. Those I/O could be networked I/O or could be, physical I/O. It's completely independent from the operating system. So what's happened is that you don't need the patch. You don't need nothing to patch. You just need to coordinate the communication between this particular, let's say, accelerator or offloader that is in the FPGA and the CPU. Clearly, the real-time patch, the support of an operating system inside the CPU is still is definitely needed, because given 100 in terms of application, I would say the accelerated part or the deterministic part is maybe 20% of that, but is extremely critical. This portion is basically offloaded in the FPGA. The rest is done traditionally in the CPU. So you will have the patch, but in addition to that, you have the precise determinism created in the FPGA. So the FPGA could host an algorithm, a networking system, or even a soft processor. So, for example, if you need to offload a portion of your computation and say, oh, well, you know what, if I would have an additional processing system, that could make my life a little bit easier. So we have the ability to create an instance of a soft processor, transferring this instance into the FPGA and having this computation running alone. As for example, you included an additional CPU in the system. So it's a very, let's say, powerful way to design your system. The important things that you have to have in mind is starting with partitioning your system. Say, okay, I would like to define this particular portion that interact with signals in a very precise way. So I'm going to offload into the programmable logic. I would like to use this particular algorithm inside the CPU because it's not time critical, or it doesn't offer, it doesn't require a certain computational ability. When you partition your system in this way, I can guarantee you that the result is really phenomenal. I mean, it's a public information. Many of the say, top vendors of robots are using this particular technology inside the system. And that's the way how they can achieve basically such kind of performance. Coming back to your your example of things that are moving, correct. Robots that are moving, robots that are working, robots that are operating in a space, they require a massive amount of information from sensors, and those things are basically not taxing the CPU that is used to coordinate them. But the sensors are acquired in the FPGA, processed locally with the algorithm, and the pre-processed, or let's say the bulk of such sensory information is then transferred into the CPU. And those type of mechanisms are using shared memories, other type of, I would say, I can elaborate more on that, but fundamentally it's a tight connectivity between the programmable logic and the processing system, such that the latency is minimized.
Okay. Okay.
But
Yeah,
more you learn about this technology, and more you will see how the beauty of applying those elements, because fundamentally it's simplifying certain type of approaches, partitioning the system, dividing. It's a divide and conquer approach.
Yeah. I've never developed a robotic system by taking that into account, but I can see the difference and also the advantages. So
there are many advantages. I mean, those advantages are coming, with a certain, I would say, understanding of the fundamental technology that is behind. So there is a certain amount of learning curve, and I'm assuming that it's not. I mean, it's something that we need to take into account. But the learning curve is very much simplified. And because we are offering also mechanism within the KR260 and the Kriya SOM that are closing or reducing the gap between the roboticist and this particular technology. Yes.
Okay. Then you are going to the point of programming these kind of systems. Yes. And then so you mentioned, for example, that the KR260 has native ROS2 support. So what does it mean? That it's ROS already installed inside, or it's running already in the hardware?
We need to define, I mean, a little bit the native support. We are talking about acceleration. Okay, first of all, we are talking about determinism. We are talking about real time. We are talking about a technology that is, the programmable logic, the FPGA. When we are saying is ready, is ROS2, natively supported. This means that you can install ROS2 in the KR260 as a standard ROS2 installment. Just simple as that. But behind, you might ask, how can I enable a roboticist to use and accelerate a specific ROS2 application with this technology? That's what we mean in terms of ROS2 enabled. We are offering a framework that is called the KRS, Kriya Robotics Stack, that extend ROS2, operating on Qualcomm and AMD, and creating all the different, CMake verbs and subverbs that allows the ingestion of those accelerators into ROS, and the combination of a ROS package connected to the accelerators in a native way. That's what is a paradigm, is a paradigm shift. So instead of saying, oh well, you know what, we have this accelerator, you have to do this and that, it is directly connected with the ROS2 development mechanism and procedure. You just invoke Qualcomm, build, and giving the particular firmware, giving the particular accelerators, and the system automatically create the packages, create all the elements that are required to be then deployed in the final system.
In the FPGA part.
In the FPGA, in the CPU, in all the system, it's the full combination.
The full combination.
It's the full combination.
Okay.
So it's worth, I mean, for a roboticist, in my opinion, it's worth spending a little bit of time considering this particular technology, because you will discover something that you say, oh, well, until yesterday, for me, this was a very difficult problem to solve, synchronizing those things, synchronizing the data acquisition with the robotics with a specific packet. Today, with the KR260 and the KRS approach, I have a much more simple and a much more efficient mechanism to have those elements, to use those elements. So, for example, you acquire signals out of a LiDAR. You want these signals processed very, accurately and transferred in the CPU. What the KR260 allows you and KRS allows you to do is exactly this type of combination. There is a platform elements that is the fundamental programmable hardware that goes there, and then there is a mechanism to design this platform. And you design your algorithms in the very same way as you are designing a specific, I would say, C or C++ algorithm. This particular algorithm is funneled into, the KRS, and KRS is just a Qualcomm whatever type of accelerator, and is invoking all the compilers behind the scene. So it's invoking the platform compilers that creates the hardware, it's invoking the compiler that transforms your piece of software into a hardware, is linking all together and deploying the elements in the package. I would say it's longer to say than to do this.
Yeah, I understand. And it's because the tools already provide to you all this automatically. So you only need to invoke those proper commands and maybe to create some config files indicating which parts go to the acceleration part.
You have to create the accelerators first of all. I mean, the accelerator, you can take, for example, let's say a rectify or let's say a video portion. Okay, so it could be rectifying an image coming from the camera. It's a very simple operation. Okay, it's a very simple or sort of filter, and you design this particular operation, or you extract this particular operation out of the perception packages. You basically add a couple of pragma definitions to your code in order to instruct the compiler, oh, hey, put these particular things in hardware. Okay, and you provide basically a connector that is a piece of let's say C++ code that attach your package into the hardware, and then you compile these particular elements via Qualcomm. So all the compilers are basically invoked behind the scene. And the package is then prepared and cross-compiled, and you can transfer the things into the board. Correct.
Okay, great. So the procedure will be, so we have our normal development machine, which is a Linux machine, and then we beside it we have the Kriya, for example, which is inside our robot. Then we use the Kriya robotics stack in order to cross compile in our machine the code, and then we send it to the Kriya machine. Okay, and then that's it, and then it runs directly.
Then it runs. I mean, that's basically the preferred way to do things. Yes, correct.
Okay, and
but you can also compile on target if you want. I mean, you can create your accelerator outside the system. I mean, I can spend more and more, but I would say the most efficient way is passing through KRS, cross compiling, and transferring the cross-compiled system into the KR260. Correct.
Okay. And does it exist any documentation already ready? There
is a documentation. If you just Google KRS and then you see KRS Robotics or whatever. So there is a website in which there is a full documentation how that works, the install procedure, how this particular system, is deployed, how you can, program the SD cards, so on and so forth, what type of operation are there, and it's all open source.
And I have seen some examples, right?
Yes, there are some examples.
Also some examples.
We do have basically a forum that is the Hardware Acceleration Working Group. As you mentioned before, it's we have one of our fellow guys that's it's Victor Majorel-Gilches that's is basically hosting in the Hardware Acceleration Working Group, and many of those elements you can find a lot of explanations over there, because we have those recorded sessions, and the material is basically available in GitHub. as an open source material. That means the accelerations, so the Qualcomm accelerations, in the firmware, as well as, I would say, all the steps and procedures that are fully documented in the website.
Okay, yeah, then I will check myself also and put a link into the
Yes,
show
please
notes.
put the link
Yeah,
over
yeah.
there, and I can give definitely the links verbally, but it's better that you put the link in the system. Absolutely, it's basically GitHub.io/KRS, so it's xilinx.github.io/KRS, and then you will find all the definition and the concept about KRS.
Okay, then let me put a concrete example. So this is for the audience, right? So the audience has of the podcast has different levels. So maybe some will have get it already, but for some other people, it's depending on the ROS level. So
Absolutely.
let's put a concrete example. Let's have the navigation 2 stack.
Mhm.
So we want to run the navigation 2 packages inside the Kriya. So
Mhm.
we have the source code of the
Okay.
navigation 2 stack
Mhm.
created by the awesome developer, one of the creators, but the main creator, Steve Masensky. And then we have this package in our computer. Then we should, in order to make it run inside the Kriya,
Mhm.
inside the KR260, we
Mhm.
have to cross-compile it, right?
Yeah, I mean, you basically you can cross compile, you can install that directly. I mean, anything that goes into in the CPU is basically a sort of no-brainer. Is a start.
Oh, okay.
Is a standard process.
So we can
No,
go there and do an apt get
you enable,
update.
you go there, you do whatever you need. Then the next
Oh,
step
okay.
is saying, oh well, things are running in a processing system, everything is fine, everything is standard. You know, there is no difference, absolutely no difference. You do exactly what you are doing with an embedded platform, any type of
Normal.
embedded platform. This particular
Okay.
embedded platform is not in any way different. Okay, so up to this point, is everything ready. There is Ubuntu is running there. You do whatever you need. You can compile on target, whatever you like. At a certain point, you are saying, okay, I have now to. The first thing you should be doing is basically trying to, assess the performance. Where is the bottleneck? So the first thing you should be doing is trying to trace, or let's say in a certain extent, to try to understand where the most critical part is there. ROS2 allows, for example, LTTNG as a tracing tool, as you might know. So is the Linux tracing tools new generation that you can use in order to insert a specific, I would say, measurement point in your code and identifying where is the bottleneck. The bottleneck could be in a communication with DDS. The bottleneck could be in a scheduling process. The bottleneck could be in passing a specific topic between nodes. So at a certain point, you identify with not to a place in which, I would say, 80% of the load is over there. It could be a big module, it could be a small module. Definitely, I mean, when we are talking about acceleration, we should not say, oh, we are accelerating everything, because it doesn't really make sense. Acceleration has to be something that is specific in order, to create and provide the proper performance. So you instrument your system, you go through this particular benchmarking, and you identify within NAV2 the module that needs to be accelerated. You basically rewrite the little piece of this little piece of code. It's just a C code. You add those pragma, you add those connectors, and then you recompile the system. And this is what's going to happen. That's with NAV2. Very often you have much more simple elements. You need a new sensor, you need a new element that's not necessarily as complex like NAV2, but you need acceleration, because any additional sensor you add to your robotic system is basically creating additional load to the CPU. So it's better removing those loads. In this case, you design your driver. You take your driver, let's say the code that is responsible to process those signals. You created a specific accelerators that is no more, no less than a set of C, programs or C++ programs, you compile them and you use them in the system with this particular connector. So instead of, you know, creating all those measurement elements, the tracing, those kind of things, if you have a new sensor or new elements in which you have full control, it's better that you go directly with the acceleration. You design your system, you compile the system, and you connect it.
Okay, okay.
What
yeah,
I would say, it's sometimes is more difficult talking about these things than doing. Doing is easier. That's
Yes.
what I'm saying. And
like
we don't have a lot of documentation, a lot of information, elements that could be used to, you know, to fill the gap. The roboticists shouldn't be, you know, I would say use this term, scared about this new technology, because there is nothing in particular that's you know, a pushback or is impeding you. It's just a way of thinking, understanding that, you know, dividing your system in small manageable pieces allows you to improve the performance using the hardware acceleration. If you have an already available package, nav to the perception, whatever that is, we have an example, for example, with the SLAM, with the vSLAM that we put in the public domain. So as an open source. So we are basically accelerating SLAM inside the programmable logic. Is a full example. And what we did is, with a partner, is analyzing the code, identifying the portion that need to be accelerated, instrumenting the code and understanding where is the bottleneck, extracting the specific portion, recompiling that, and that's all.
Exactly. So now I think I got it from your explanation better. So any algorithm, actually, you don't need to redesign it in order to execute it inside the accelerated part. The only thing that you will need to redesign is when you have several parts, and then you must decide which ones are you going to take out to put it into the acceleration part.
Correct.
So and that's the
That's
different mentality that requires from us, the developers, right? To think in this way, instead of putting everything inside the CPU and one thing after the other. Then say, take, oh, this part, let's put it there because it's more efficient. And then the rest continues, but there has to be some connection points.
Correct.
So you need to think about your algorithm
Correct.
having those connection points, but that's all.
That's all. Think about, I mean, the best robot is I mean, no offense, but is a human person. So the brain of a human person is a very distributed parallel system. So that's the way you should be thinking. I mean, there are things that we are doing unconsciously, and we are doing that in a very, you know, fast real time, because we have a little piece of our brain that is dedicated to this particular function. So if you assume this type of circumstance is not a serial machine, is a very parallel machine, the best robot in the planet that is still a human being. So that is the approach. So distributing the computational elements inside the specific silicon and using the programmable logic at your advantage. So you don't need to recreate everything. You need just to, you know, focus on this particular portion, and there are just part of that that's requires a little bit of, you know, redesign, reprogramming. To make things simpler, we offer already accelerated libraries in our packages. So there is what is called the Vitis accelerated libraries, are open source again. We can also provide Vitis is our framework, is our design framework. So we do have a design framework that is called Vitis. Is the compiler, is the element that is required to generate the embedded platform to compile the full code. So it's basically our product. Under this umbrella, there are a lot of open source projects that are offering libraries, tools, elements that are used in traditional and classical embedded design. But in addition to that, we are offering the libraries in C and C++ code that could be used, I would say, directly to implement those accelerators. You can, there is not something that you have to reinvent or to redesign from scratch. We already have those libraries that could be used out of the box. It's
Okay.
also a very good way to learn about this technology.
Okay. Yes, I will put again another link
Again, the
to
link on
those
that. Yes,
to
correct.
those
Correct. Because
examples. So,
many of those informations, are put in the open source world, but you need to connect the dots. So
mm,
my answers here are related to connecting the dots. Why, how, where, those kind of things.
yeah, and that's why we are having this conversation here
Absolutely,
today.
absolutely. Because I mean, it's a great technology. There is a lot behind. There is already a planet of things that are ready to be used. In our standard, it's just, I mean, it's just the way how those things are basically connected. So how this hardware world is going to connect with the software world and with the robotics system.
And then, so then, and as you mentioned, I think that we have all the information. So let me ask you, what is your opinion about the role that this hardware accelerator will play in robotics in the close future? Because at present, there is almost none. So almost nobody is putting this kind of hardware accelerated in the robots, just in a few very specific
Yeah.
cases. What is your opinion?
I mean, I have definitely a strong opinion about that, but
Go
to,
ahead, go ahead. That's
to give
that's
to
why
give to give to give you the opinion, I fundamentally believe that the hardware acceleration is the element for the future. The reason is we already know that CPUs in terms of clock frequency and are not scaling very well. So you see more and more that new products have multiple CPUs, multi-core, many cores, heterogeneous systems. Okay. The hardware acceleration is a part of this particular heterogeneous system. That's the purpose of hardware acceleration is creating in hardware and offloading in hardware what the general purpose CPU is not, is not required to do, because it's in general, I would say, it could do many other things much better. The hardware acceleration is fundamentally for the future, because robots today robots are very clumsy, if you pardon me, and to give them the ability to interact with the real world much better, and in combination, I would say, with the new topics like AI, you need a partition between having certain operation accelerated and offloaded as close as possible to where the signals are operating, where the actuators are operating, and that's where hardware acceleration is playing a fundamental role. The other part is, removing certain bottlenecks in the standard processing systems, and for that reason, more and more look for example the autonomous, driving or autonomous navigations. It requires a massive amount of parallelism, and that is achieved just, creating a specific accelerators. Is the accelerators, based on a programmable logic? Absolutely, yes. Is the accelerator, used with other type of technology? That is also possible. But the fundamental element is the combination of all the technology at the system level, and that's what hardware acceleration is going to be there. In one feedback that I can tell you, for example, the amount of people that are attending the hardware acceleration working group it's in general very high, because there is not just interest, it's becoming a reality. There is basically the future is related to accelerating things in hardware. The technology is a combination of the different ones: CPU, FPGA, and other technologies. Yeah.
Oh, okay, awesome. So, listeners of the podcast, then we have to start thinking about learning how to move our programs into hardware accelerated systems.
Yeah.
So I
And
think that,
one thing that I would like to add is that this particular technology allows you, for example, to go in the direction of safety, because many of the robots will require safety enabled solutions. So the combination of programmable logic in the CPUs gives you the ability, to create diverse systems that I don't want to enter in this particular, I would say, topic that is very specialized, but more and more robots have to be, designed according to a functional safety system. And this particular, I would say, technology enables you to move in this path, because it's, we already have the certification. Well, there's already an infrastructure behind it. So it's not just acceleration, it's not just hardware acceleration, but it's specifically even providing the concrete elements for ensuring functional safety in a robot.
Okay, so well, you are opening a new
topic. I'm opening a world of elements. It's as I said, it's worth to mention, to look to this particular technology, because it's different.
Yeah. No, but this last point that you mentioned about the safety, that's a real concern in order to produce products for the masses. That they need to be safe, and they need to, in order to be safe, they have to be certified that they are safe. So this is one of the problems. Actually, there is, for example, the Apex AI company that is producing a ROS2 version certified for autonomous cars. So that's a whole company that is devoted only to that subject into this. So if we want to create robots of the future for the masses, for the public to be used there and to certify that they are safe, then what you are indicating is that going into that direction is a way of getting this certification.
Yes, because it's already enabled for the functional safety portion. I mean, in addition, I'll give you an example. In addition to the A53 cores, we have basically an ARM core inside this particular Kriya device. Okay, but we do have a couple of real-time processors that are basically designed for functional safety. They could run in what technically is called a lockstep mechanism. So it's basically a duplicated system. So it's a redundant system inside this device. The device has been qualified according to a functional safety standard like the 61508 and the 26262 for automotive and industrial application. It has been certified for the machinery directive, the place where the robots, the industrial robots are there. The combination with the programmable logic allows you to create a specific, I would say, additional elements in the programmable logic, like, for example, another processor. So having those diverse systems allows you, in case of failure, to avoid what are called the systematic errors. So there are a lot of things, and the robotics community, in my opinion, should be educated a little bit more. It's not a fault of the robotics community, but it's because functional safety is so specific, and I would say, and in a certain extent, so dedicated that there is an educational process that's is needed. But as I said, we have material. We are hosting a lot of, we are doing a lot of activities in direction of functional safety. We are hosting every year a big event in which we are presenting what is possible in terms of functional safety. Many of the, I would say most of the primary robotics companies are using our technology for functional safety, not just for the robotic part, but in addition to that, to ensure functional safety. So it's a world of things that need to be explored, in my opinion.
Yeah, you said, well, that we need to be a little bit educated in that sense, because we have been so worried and concentrated on making the robots do what they are supposed to do. Yeah, that's a very big task, exactly. So, but now we are reaching to with some results, not that many that we would like, not that many that we would like to have, but some results, and now we have to start thinking into that sense. So functional safety is the key word, okay, that you have been mentioning, and that so the audience maybe is the first time that they hear, so you can start thinking, audience, about those keywords, because we are going to need it for the close future.
I'm encouraging to think about this direction, that functional safety is becoming pervasive. In addition, I would say, to AI and all those kind of things, but definitely consider this portion.
Okay, then this is all. Giulio, thank you very much for coming to the podcast.
Welcome. Thank you.
Thank you very much, and see you around the world, maybe at the next ROSCON.
Absolutely. I'm really keen to be there, because it's as I said, it's absolutely a very, very interesting place. Absolutely top-notch people. Very glad to be there.
Awesome. Thank you very much.
Welcome.
And that is all for today, ROS developers out there. So I hope that you learned a lot about those topics, accelerated hardware, functional safety also a little bit, some points, but that is all for this podcast today. So if you like it, then give us 5 stars wherever you are listening to this podcast. And yeah, that's all. So see you next week with a new lesson from the experts. And until then, keep pushing your ROS learning.